We're here to go answer questions about the homework, discuss the homework. And so let's pull up the homework and see what it is. Or you don't even know where to begin to ask.
So A and B represent different. So
what they represent are PZ orbitals sticking out of the page. PZ orbitals sticking out of the page. So they're going to form pi bonds.
So A would represent a carbon and hydrogen atom, correct?
Forget the hydrogen. And the reason is, if you want to go into the details, so here's the actual structure. And if you go back to the last thing we talked about on Wednesday, about this basis set of orbitals, we're going to use px, py, and pz. It's like p orbitals oriented along x, y, and z. Okay? So you're going to have, on each carbon atom, you'll have a p orbital oriented along x, and a p orbital oriented along y, and a p orbital sticking out of the page, which I don't know how to represent. And that's our pz, and that's the one that we're worried about. So these other ones are doing the sigma bonds. The ones that I drew are doing the sigma bonds, which are going to be the stronger bonds. Therefore, the splitting is bigger, and they're going to be at energies further away from the Fermi level than the pi bonds. The pi bonds, which are sticking out of the page, and if you look down on them, they just look like circles, right? Are going to have a weaker bonding because they're not like pointing towards each other, or they're not dealing with the hydrogen atom. They're just bonding to carbon atom to carbon atom.
So is the band gap smaller on those, or?
Yeah. So T 2T is, you can think of as the band gap. Right, that's always a splitting, 2T.
So you have less potential energy is, okay, so you need less energy to be able to get into those different bonds.
With respect to the Fermi energy, I mean, the Fermi energy would be right at 0, and then, at plus T pi. So you've got the T, and here you got a single and double bond also, so it's even trickier, right? Now if I call this, if the bonds are all the same, then actually you don't have a band gap. So this is not a good problem to discuss. We should go back to our that problem you did for homework 1, which I guess I still need to grade. Sorry about that. What I want to say, all I want to say is that the important bonds to us, the ones that give you the lowest energies near the Fermi energy, are going to come from these pi orbitals sticking out of the page. And that's all. So that's, if you're going back to your original question, that's what your A and B stand for. Down here, your A ket and your B ket, they just stand for a PZ orbital sticking out of the page.
Okay. And then, so lowercase n represents the different lattice points?
Yes.
And so then capital N is the total number of lattice points?
Yes.
So capital N is a constant. Lowercase n is going to be changing, which is the one where we're doing the summations.
It's your index, yes.
So when you do, so the first thing that we do is change, we do like a Fourier transform, and then get everything into momentum space.
Like you make the block sum basis. Yeah, I think so. That's what. Yeah,
Okay.
Construct the block sum basis, A of k and B of k.
So you're doing that, and so then when you do the inner product between one of the diagonal matrices, so like an SK,
AK.
Or sorry, I'm looking at the notes. Yeah, AK. So
right.
if you do one of those,
yeah,
you get two summations. So you have to when you're doing the two summations. So you're fixing one location, and then you do a summation over all the other ones, and then you move that. So it's like two different for loops. So it's like a what do you call that?
Yes. Yes.
So then, but then when you do that inner product and the two indices are different than each other, then it's just going to be 0. So you're only worried about when they're the same.
Gives you a Kronecker delta function.
Okay, that makes sense. And then my question is, when I'm looking on the notes, you have the summation of just n, and that is just going to give you n.
Mm-hmm.
But why isn't it n squared? Because you have nm.
Because the Kronecker delta killed off one sum. The Kronecker delta only gives you an n. It kills off one sum. So if you fix n and you have a Kronecker delta in your sum, then that sum becomes just 1. M only gives you something when m equals n, and you fixed n, so it collapses that inner loop, if you want to think of coding. An inner loop and an outer loop.
It kills the inner loop?
Yeah. I mean, usually you do the inner loop first. That's what we mean by an inner loop, right? The inner sum and the outer sum. So if you have a Kronecker delta, you fix the outer index, and then you have a delta nm, and say m is the inner index. There's only one. You only get one element from that inner sum when m equals n. So the Kronecker delta will collapse the inner sum, and then you're just left with the outer sum. Because they're sigma bonds. They do. And again, if you think in terms of symmetry, those on the hydrogen atom, there's only an s orbital. And that s orbital will have no matrix element to the pz orbital on the carbon. So it forms its own subspace. The pz orbitals don't have any matrix elements to either the px, py, or s. So it's like they form their own little subspace. And that happens to be the subspace that's closest to the Fermi level. It gives the bands that are important for electronic conduction. So that's why we're just looking at the pz orbitals on the carbon atoms.
So you're telling us to forget about that e to the ik.
That extra phase factor, yes.
You're telling us to forget about that. So then when you do an off-diagonal matrix element, is it just going to be m minus n, and then you're not going to have that minus 1/2 then?
Correct.
Okay.
And so if you go back and look here, and I'm looking at, say, the matrix element, the off-diagonal matrix elements of A, right? So I'll get one matrix element from here to here, which will have this in it, right? And I'll get, and in this case, B will have the same phase factor as A. So I'll have an e to the ika times n minus n, and there will be no phase factor for this matrix element.
You said that one more time? So wait, I'm sorry. When you start saying
sorry.
I can't really visualize it.
So for these two guys, looking at this matrix element, I'm going to have your minus TD, and then I'm going to have this e to the ika times n minus m, but in this case, this is the index of the unit cell, and they're both in the same unit cell. So m equals n when they're both in the same unit cell.
So would that be called the basis? Is that the correct terminology or no?
What would
basis is I'm trying to get my terminology. So it's like you have different lattice points, and then the basis is considered.
Oh, yeah, that's the terminology that's used. So the lattice has a basis, and there's 2 atoms per unit cell.
So when you say basis,
that actually means something than what you talk about in quantum mechanics. So the crystallog, when they talk about a crystal, you have the lattice, and I think mathematically the lattice is just sort of abstract points in space that represent the periodicity of your crystal.
So each repeating
Each
repeating basis is a lattice point.
and so like if I want to show the lattice points in this case we're choosing to be A. So there's a lattice point, here's a lattice point, and here's a lattice point. Those are the lattice points.
Okay.
And then the basis, I have 2 atoms for each lattice point. So each lattice point consists of 2 atoms. There are 2 atoms associated. That's the way to say it. 2 atoms associated with each lattice point.
Okay. So you're just worried about the atoms. You're not worried about those bonds. You don't include the bonds into the basis. If that even makes sense.
No, you don't. That's
Okay.
not part of the
Sorry,
concept.
I don't know.
That's a whole different concept.
Okay. Got it.
Bonding and basis is just atoms associated with your lattice point.
Got
In sort of the crystallographer sense.
Okay.
And it means something else in the quantum mechanics sense. But anyways, anyway. Okay, so at any rate, going back to the matrix, what's really relevant for your homework, if we're looking, okay, let's be specific. If we were looking at, AK, H, BK, right? I mean, this is what we need to look at, right? This is what we're talking about. Yeah. And then you expand out your AK and BK sums, and I wish I'd left a little more room here. So if I expand them out, I'm going to get a term when I do to this matrix element here that I've written down here. I'll get that term. And m equals n, so this phase factor is just 1. So there's no phase factor associated with that. Plus I'll get one going to the left. Right? I'll get a matrix element of A bonding to this guy, to its nearest neighbor to the left. Right?
Wait. So okay. So that's the other.
The other nearest neighbor. There's 2 nearest neighbors for every atom. To the right and to the left.
So is this the Hamiltonian matrix? Is it like a really big one, or is it just because somehow we've got it to a 2 by 2?
Yeah. For each k, it's 2 by 2. For each k, it's 2 by 2. Because there's only my basis is for a given k. My basis is just two orbitals, A of k and B of k.
So this is kind of the nearest if that's the correct terminology, the nearest neighbor, which allows us to have a 2 by 2 instead of the huge matrix to have the relationship between all the different.
No, it will always be 2 by 2. If you got a basis, if your basis is 2, if you got 2 things in your basis, your matrix can't be bigger than 2 by 2.
So we're only considering, because
even if I had matrix elements going from here way out here, it would still be 2 by 2.
But then you're including a lot more atoms. A lot more.
I'm including all the atoms, right? Because this is A of k is an infinite sum. It includes all the atoms. That's 1 over root n. Sum over all the unit cells, sum over every orbital n times its phase factor.
Oh, okay.
That includes every A atom in your infinite chain. And B of k includes every B atom.
Oh, okay. So that's how you're doing it. So you're not doing it by individual atoms. You're doing it by the set of A atoms and then the set of B atoms.
Because they repeat. I mean, every unit cell has the same A atom and the same B atom.
And you kind of consider there's no ending point, so it's kind of like infinity for n.
And, we discussed those periodic boundary conditions. You don't have to think about it when we do this. The periodic boundary conditions are...
Okay.
Since it is periodic, that's why we are writing like this. As block some function.
No. I don't know. I mean, the periodic boundary conditions at this point really aren't. They're kind of buried in there somewhere, but they're really not important.
What's the reasoning? So if it's a periodic, that's the reason we're using.
So there's two
block sum.
periodicities. One, is periodic every unit cell, right? There's one periodicity. When we talk about periodic boundary conditions, it means on this phase factor e to the I k n a, for some very large n that we eventually let go to infinity, we say that 1 is equal to e to the I k a times this n, which eventually we let go to infinity. So we're implying this kind of fake periodicity a couple miles away.
Okay.
And this is just sort of an accounting procedure to keep track of certain things when we convert sums to integrals and stuff like that.
So if we were not to use the block sum and we were to use the other method,
Then you would have an infinite matrix.
so our Hamiltonian matrix
It would be infinite,
'Cause we have to
in this
include
case,
every
infinite tridiagonal. Yeah.
okay, that makes sense.
So, I mean, it's like, how do you deal with, as an electrical engineer, with a periodic signal? Right? You don't worry about all time. You just say, well, it's like this delta function in omega. It's a single frequency tone. You don't worry about its fact that it's infinite.
Okay,
It's just repeating.
that makes sense.
Okay, so so we're taking the matrix elements in this block sum basis, and the only thing different is the way the phase factors come out. So let me just give myself some more room to work on here.
It's true to say if we neglect any reflection, and this is the periodic condition. Because only if you don't have any contact here.
Well, there's one more possibility. That's the quote open boundary conditions, which we'll talk about in 212.
When it's not open, then it's
You can have open, periodic, and closed. Closed is like particle in a box.
but in the closed we also have reflection.
Yeah, you have then you have a true standing wave.
And here we don't have any reflection.
Here you don't have any reflection. So if we go back to our matrix element, what are we going to have? So I've got 1 over n. If I expand out those two block sums, I was looking at what was I looking at? AK, HBK. And nice, the only way you can evaluate this is to expand out the block sum, and so then you have some 1 over big N, some NM, AN, H, BM, E to the IKA times M minus N, right? That's what you're going to have. And then again, so now let's fix N. We'll fix our outer loop and do the inner loop, which is M. All right. We'll do M. And so there's going to be this is going to give me, I'm fixing N. I'm fixing my A atom. And I guess the way I had it set up, I had an A, and what do they have? A double bond B. And this is in the same unit cell, and then over here I had the other nearest neighbor in the unit cell behind it. So these two guys are in unit cell N, and this is N minus 1, right? That's the way the indices are on the unit cells, right? And so so I get two terms, and this matrix element is, what do we say, negative TD, and this was negative T, what do we call this? TS for single bond? TS maybe? It's a single bond and double bond? Yeah, all right. And so this is going to get, when they're in the same unit cell, then I have delta N comma M, and the matrix element is negative TD. And the phase factor is 0 because M equals N, right? So that's the one for the same unit cell. And then I have delta, so I'm fixing N and moving M. So M is equal to N minus 1 and times minus TS. And now my phase factor is E to the I, K, A. And what have I got? I have M is N minus 1, so I just get a minus 1 in here, right? If M is N minus 1.
So this is why you can say, because in the notes you have N is equal to N minus 1. You kind of relate the M to the N in order to reduce it further.
I mean, that's what I did with my chronic. That's what the Kronecker deltas do. I'm getting the Kronecker deltas from that matrix element. Those are the only two matrix elements in the nearest neighbor model.
Okay.
Again, so the Kronecker deltas are collapsing the sum over M and just giving me two M's. One when M equals N, and one when M equals N minus 1. So the inner sum, I just get two contributions. So this is all still in, say, big brackets. So the Kroneckers collapse. If I've already taken care of my Kroneckers, I can now get rid of it. I've already taken them into account, and now I'm just left with my sum over N, and this 1 over N. But if you notice, the argument in the brackets is not a function of little n, right? It's independent of little n, so that's why this sum just cancels out the normalization factor, and I'm just left with the thing in the brackets. And that is my off-diagonal matrix element. So the Kronecker deltas collapse the inner loop, the sum over M. And once I sum over M, they're gone. The Kronecker deltas are gone. And then I just am left with that outer loop, sum over N, which is just, since now the argument is no longer a function of N, that just cancels off the normalization. And so, I don't know, what were the questions? Contract matrix element. And then I guess I would probably want to like simplify it by factoring out an e to the I something. What would I want to factor out? E to the minus IKA over 2. So that's e to the minus IKA over 2 times minus TD e to the plus I KA over 2. I guess this is not going to help you in this case because the t's are different. Minus TS e to the minus I KA over 2. If the t's were the same, I could now write that as like a sine function, but the t's are different. So I'm not sure if that helps me at all. I haven't done this problem in a while. At any rate, this is your off-diagonal matrix element. So in the red bracket, I factor out an e to the minus IKA over 2. Right. So then I got to multiply this term times an e to the plus IK over 2 to kill off the e to the minus IKA over 2.
Oh, so you kind of like artificially.
And if those t's were the same, then I could combine everything and turn that into a sine Ka over 2, which is what happened in, I don't know, a class or homework or something, or the class problem.
Yeah.
The two-band model.
Yeah.
But now the t's are different, so they're not going to combine.
So
Yeah, you get the dispersion relation,
okay. I don't usually find the name of the
and then
function there.
you find that. I mean, it should look like, let's see. Oh, right. So another thing you can make use of for sanity check and make sure everything is. Use something we talked about before, right? This is going to be a 2x2 Hamiltonian. right? As we've said, H is a 2 by 2 Hamiltonian of the form, they're both carbon atoms, so they both have the same diagonal energy, right? And then you've got some function of K on your off diagonal. This is the generic form, and so, as we already said, for a 2 by 2 Hamiltonian, E is just equal to, in this case, since the epsilons are the same, epsilon plus or minus magnitude of this complex thing that's on the off diagonal. And so it's just a matter of finding the minimum in K of that complex thing, the magnitude of the off diagonal matrix element. That's all it is.
Is the diagonal matrix element always going to be a constant?
For nearest neighbor, a nearest neighbor model, yeah. When you go to next nearest neighbor, it becomes K dependent.
So, because the diagonal elements are just the same. It's the same atom, so you're referring to the same atom, right?
Yeah.
So it doesn't involve any other atoms. It's just
Not in a nearest neighbor model. Yes. If you go to a next nearest neighbor or beyond, then you actually are bringing in other atoms, and it becomes K dependent. Because if you go back and look, if you go back and look at the picture, I got to kill this. So if you go back and look at the picture here, in a second neighbor model, I would have a matrix element between A here and A over here. And then there would be a phase factor, even for the diagonal matrix element. So AK would include this matrix element from here to here, which now has a non-zero phase factor. Right? The phase factor would be e to the IKA, since it's a 1 unit cell away in a second neighbor model. When you calculate, we call the diagonal matrix element AK, H, AK, and these AKs have a sum over all the A's, right? And so the part of, one sum will have a matrix element with this term in the other sum.
So is this like, I don't know how many questions I should ask about this. I don't know if we're gonna do this later, or if I should.
We're not going to do second neighbor, but it's good to keep in mind that if you go beyond, it's only because we're doing a nearest neighbor model that the diagonal elements are not functions of K.
You could do a next. What is
Yeah,
it called?
next nearest neighbor, second neighbor model,
A second neighbor.
third neighbor, fourth neighbor. Yes.
You could do that on this.
Yes.
So what are the advantages of doing that?
It can give you a more accurate model, because in reality there are non-zero matrix elements between second neighbor atoms, but then becomes computationally more difficult. So it's a trade-off. You always use the simplest model you can get away with. So if this satisfies your needs, your nearest neighbor model, you go with it because it's good enough. The good enough principle.
Yeah. Can you talk about gamma points and stuff? Because I'm pretty lost when it comes to when you start talking about that.
Yeah. So in these 1D models, our quote Brillouin zone is a 1D, and it just goes from plus and minus pi over a to pi over a, and this is your K axis, this is your energy axis, and this is at K equals 0. That's called the gamma point, and out here at the Brillouin zone edge at pi over a and plus and minus pi over a, those are X points. So they're symmetry points, and they have the same symmetry. So when we go to 3D, for X equal plus or minus pi over a, Y equal ky equal plus or minus pi over a, or kz equal plus or minus pi over a. They're all called x points. They're all by symmetry equivalent points.
So would
But gamma is gamma, because k equals 0 is unique.
so when k equals 0, that's the gamma point?
Yeah.
So at the gamma point, is that the location of where the lattice point is?
Now, this is k space.
So this is something totally different.
This is
Okay.
k. This is your k. This is right. I mean, we know that, this is a sum over all lattice points. This is a sum over all lattice. So it's like a
kinda
Fourier
like-
transform.
Okay, so now I'm in like frequency.
Yeah, you're in the frequency domain.
Okay.
You
So
can't
then-
ask, well, what time am I at? You did all time. You did a Fourier transform, right?
Okay. Okay. So then, what does it mean to have a negative value for k? Does that mean anything?
I mean, we could, so we calculate some dispersion, some energy versus k relationship, and we plot it like this, but it's periodic. So we can choose any part of the period, So we could have chosen from 0 to 2 pi over a, like that, if we wanted. It's entirely equivalent. But people always choose this, and I guess it's, in all these simple models, if you're in a negative k point, then your velocity is negative. If you're in a positive k point, your velocity is positive. It's kind
So
of
it's like a
more
direction.
intuitive. No, well, yeah, I mean, momentum, as we were talking about, is h bar k, right? That's supposed to be k. Sorry, h bar k. So if k is positive, you're moving forward. If k is negative, you're moving backwards in these simple models. And actually, you got to look at the group velocity, which is this d dk, which is the slope. But that also gives you the same thing, because over here the slope is positive, and over here the slope is negative.
So it's the Brillouin zone is essentially this. It's one cycle.
Yeah. Yep.
I'm trying to understand why it's.
Well,
periodic.
think of
So-
your discrete Fourier transform.
Okay.
You introduce a periodicity, and the periodicity is defined by your delta t, your sampling time. You sample in the time domain some delta t, and so then even if what you're sampling is not periodic, you introduce this artificial periodicity in the frequency domain of, I guess, 1 over, something on the order of 1 over delta t, and then your spectrum will start repeating, because you can't go to a higher frequency. It's a Nyquist frequency, right? Anything beyond 1 over delta t doesn't make sense. You don't have that information because you're only sampling every delta t.
Okay. And then
Sure, you
Are
all
these-
remember your signals and systems, right?
these actual lines, or are they points?
This pi over a minus pi over a?
Well, just these.
I mean,
so,
in
'cause-
1D, it's a point. I mean, actually, in all D, it's a point. So the x point, as it says, is a point in k space. So it's, there in 3 dimensions there are 6 x points. When kx is plus and minus pi over a, and everything else is 0, or ky plus and minus pi over a, and the other 2 are 0, or kz plus and minus pi over a, and kx and ky are 0.
I think he's talking about channels.
What's that?
About channels.
What
He's talking about channels.
What channels?
It says that they are the points or not.
Yeah. Is it an actual? Is it a continuous line, or
No,
is it
it's
discrete?
Okay, again, k is continuous,
So it's.
right?
continuous.
Delta k is our what did we say? Is our what is it? Pi. Is it 2 pi?
Yes.
2 pi over L.
Yeah.
L is this artificial thing after which we introduce our periodic boundary conditions, and we let L go to infinity. So the distance between K points is,
But they are discrete.
if L goes to infinity, is delta K discrete?
Isn't it?
No, it's
Oh, no,
continuous.
it's zero.
It's continuous. That delta K is 0, which means the distance between delta K is the distance between two K points. Right? K is a continuous variable. That's why we convert our sums to integrals. When we convert if we have a sum over K, we can convert it to an integral over K because K is a continuous variable. I mean, these periodic boundary conditions are just, as I said, sort of an artificial bookkeeping method. We always take what they call formally the thermodynamic limit, where you let the volume go to infinity.
If we reduce the L, they become discrete. Yeah.
If it was really, yeah, if you impose your periodic boundary conditions at some finite L, then it's discrete.
And in reality, they are discrete.
In reality, they are continuous.
Because when I was looking it up, they had like dots, and they would just use dots. They would go from the valence band, and they would have holes in the valence band, and then they'd have the electron shown up onto the conduction band, and they'd have them as different points. So that's kind of what I was trying to understand. I wasn't sure if that was.
I'd have to look at the picture. Or whether they're just representing electrons and holes that you always represent as little balls on your
Yeah.
EK diagram.
They might have been just showing that you have holes in the valence band.
That's what they were showing. So each little circle was an electron and hole.
Okay. So when you talk about the band edge, is the band edge always going to be at that pi over A?
Well, in this case, it's a gamma, right? This is, in the conduction band edge is always the lowest point of the
it's
conduction
that one.
band.
Oh, okay. So that's the.
And if for a valence band, it's the highest point. So your valence band, our two-band model looks like this. And your valence band edge would be there. Your conduction band edge is here. This distance is your band gap.
So the band gap so we've always been doing the direct. I guess there's.
Well, the two-band model gave us this direct band gap EK, and the band edges are at gamma.
And so for an indirect band gap like silicon,
Right.
what would your band gap? How would you measure band gap?
Again, it's always from maximum in the valence band to minimum in the conduction band.
So it doesn't matter the different
The
shift.
band gap is always from max, and the valence band for everything we're doing is going to be at gamma. And for silicon, the conduction band edge is somewhere out here like this. So this is how the band gap is defined in silicon.
Here in this example, the minimum doesn't actually happen at the journal, is it? Or this question?
That is correct.
It doesn't happen.
It does not. It happens at the X point. Yeah. So,
Wait, what?
yeah, so just so you don't waste a lot of time, guys. This is what it should look like. What you're going to calculate for this homework assignment should have a band dispersion that looks like this. And the band gap, the max and min are out here, and this is what's going to determine your band gap. So that's, if you do this correctly, that's what you should get. And this gap is related to somehow the difference in TD minus TS. Somehow related to those the difference in the magnitudes. And when the magnitudes are the same, you'll see there is no band gap. When TD and TS are the same, there is no band gap. So the band gap is solely arising out of the difference between these two.
So it'd be like a metal?
Yeah, it would be like a metal, maybe a semi-metal. Yeah, the bands would touch right at the Fermi level. Like what? Like graphene, yeah.
So when you say Fermi level, that's the in between. That's in between the conduction band and the valence band, correct?
Yeah, because, it's in between. The point, more or less, in between. And since the bands are symmetric, it's the point exactly in between, midway between.
So even
And
if you
when the Fermi level is there, you have an equal number of electrons and holes at finite temperature. It's
At-
intrinsic. Or
So at when temperature is 0 Kelvin, then there's
It's- yeah.
all the electrons are going to be
All
in the
the-
valence.
all the valence, all the electrons, all these states are filled. So to go back to your little ball picture, so all these states are filled with electrons, and all the states of the conduction band are empty at 0 temperature.
So if it was a metal at 0 temperature,
Well, then they just, a metal. Do you want? Okay, go ahead. What's your question?
it's an overlap. So you'll have electrons in.
Yeah.
In
Well, a
the-
metal is weird. I mean, in a metal, you're going to have bands that just cross the Fermi level like this, and so everything underneath the Fermi level is full. Everything above is empty.
Okay.
That would be, a metal is you just got bands that are just crossing. Okay, so the very last question. I never get anyone to follow through on this. So, oh shoot, I just got rid of it. Okay, the very last question. This guy, number 8. So determine the normalized eigenvectors at the conduction and valence band edges. There will be some linear combination like that, of course, where k is a wave vector at the band edges. So you already know where the band edges occur, right? We've already said the band edges are occurring out here at the x point, right? So there's one band edge, here's another band edge. Right.
What do you mean by x point? Does that just mean that
That's when k equals pi over a.
that's x point?
Yeah, that's what we just wrote down a minute ago. Your gamma point and your x points.
Okay, so you have gamma point is at the center, and then x point is on the edges.
Yep.
Okay, got it.
And so I'm saying write down, and then for your final answer, this is this last sentence everyone kind of doesn't read. For your final, expand out the block sums in terms of their definitions in problem 1. Okay, so you've got you're writing out this equation 5, and then I say, and then expand out your block sum. So you're going to have, like, if I just look, CA, and this is multiplying. The definition is going to look like, 1 over root n. So for A of k, 1 over root n, sum over n, an times its phase factor, e to the I k a n, right? Plus the other term, c b, dot, 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 dot. So that's expanding them out in terms of the definition in problem 1. And then replace Ka with its actual value. So K is pi over A, right? That's an x point. So that's e to the I pi n is your phase factor. And evaluate the exponential occurring in the sums. And people just leave it there. Come on, guys. This is our -1 to the n.
Can't see it.
Sorry.
Oh, sorry. That always happens. Where did my screen go? This is my -1. They always leave it as e to the I pi n if they even get that far. Like, come on, that's -1 to the n. Give me something, right? E to the I pi is -1. So it's just emphasizing these are x states like we talked about in one of those homework problems. Some n, -1 to the n a n. So that's going to be the form of your plus the other term. Right? You've got that b term. No one has once written it like this. They all, at best, they get to e to the I pi n and stop.
Oh, that makes sense. 'Cause it's
Just flopping back and forth every unit cell. Yep. So this is what your band edge states are in this model, and for polyacetylene, this is what they are. All right, so I guess this is due Wednesday. I think I said. I gotta get grade the last one. So I guess no further questions.
So does this mean, one last question, so if you have K, so it repeats, I'm still trying to visualize in K space how this works. So the farther right you go on the K axis,
Yeah.
you have more momentum and more energy. Well, no, that's the thing I don't understand. So you don't have,
In this case, actually not, right? Your energy is going down.
so it's
It will repeat. I mean, it's again always a periodic function in K space. So your spectrum again is, yeah, your spectrum is periodic in K space. So we just show the first period
so at zero momentum you have the most energy.
Yep.
The most energy to overcome, or the most energy that your electron has? I'm not visualizing this.
I guess usually we call, if you're doing semiconductor device physics, the band edge, you say, that's your conduction band edge. And then for all energies above that, you call that kinetic energy, the kinetic energy of the electron. So all this would be kinetic energy of the electron. So it has more kinetic energy at K equals 0 than it does at K equal pi over n.
If it's on the band
yet-
edge, it doesn't have any kinetic energy though, right?
And yet its velocity is 0 here.
Wait, what?
I shouldn't have said that. Wait, what?
It has more kinetic energy, but its
Velocity is 0.
When K is equal to 0, it is the velocity.
What's that? The group velocity is 0 right
When
there.
K is equal to
Yeah.
0.
Well, no, I mean not in general, but the group velocity is the slope, the derivative. So the derivative is 0 here and 0 here. But it has more energy here than it has here. And I really can't give you a really good physical explanation. But I mean, the same is true. It's just you flipped it around in a direct gap. You have your, come on. In a direct gap, you have something like this, where this would be 0. This is your x point. And so, the velocity is 0 here. The velocity is also 0 there, but, you have more energy.
It's just potential energy, right? You have more potential energy?
No. I don't know what to call it. I don't know.
Is this still a direct band gap on the
Yeah,
one
this
that
is
we're doing?
direct because the minimum and the maximum are at the same
Okay.
point in K space.
Okay, I just wanna
So
make
if you hit it with light, it would absorb happily.
So are these the types of band gaps used for LEDs and whatnot, or is it different?
They're all direct, like gallium arsenide, egg gamma.
So all LEDs and whatnot that emit light would be
They're all direct band gap.
direct band gap.
Yeah.
So it depends on the methods. I mean, because like the type bonding we use, we get, as you said, like the two band model, we always get the direct band gap.
Right. But I mean,
It doesn't depend on the method that we use in order to get the band gap.
well, I mean, again, that is a caricature of the band structure of a 3,5 material. So, and a 3,5 is a direct band gap material with P states of the valence band, S states the conduction band. But like an organic LED, it'll be like this. It could very well be like this, where you're absorbing out at the X point.
So when you're doing silicon, pure silicon isn't useful. It's when it's doped. It's
Not for
useful.
photonics. Not for optoelectronics.
Well, for any electronics that matter, right? I mean,
Dude.
if it's not doped,
Dude, come
it's
on.
not-
There's a multi-billion-dollar industry built on silicon
well,
electronics.
because they dope it, right? And that's
Yeah,
why-
of course. It has to be doped. N and P gives you your, yeah.
So they dope it to decrease the band gap, or do
No, they dope it just to give you mobile carriers and give you things like PN junctions, and diodes, and transistors. But basically to give you carriers that move, so to carry your current.
So if you I'm not because I'm a lot of stupid questions. I don't know if it's appropriate.
Okay, well, as far as the homework is concerned, I think we're done. We can open this up to the stupid question session now.
Okay.
Anyone who wants to stay, feel free. Anyone who wants to leave, you can, as you wish.
So is it okay if I ask stupid
Please,
questions?
yeah, go ahead.
Okay,
Everyone's
so,
free
stupid questions.
to.
So silicon by itself is just an insulator, correct?
Yeah, I mean, going between what you call a semiconductor and insulator is a bit qualitative, but it's if it's undoped, intrinsic, it's a pretty crappy conductor. There aren't many carriers around.
So you, in order to get past the band gap, you have to apply a voltage which gives it energy to.
Okay, now we're going into
circumvent-
device physics, right? You've got your conduction, your valence band edge. We just go back to these simple diagrams. Your conduction band edge. If it's intrinsic, right, my Fermi level is somewhere right around the middle of the band gap. If I dope it, then I'm going to move it, that Fermi level up here, and I'm going to have a bunch of free electrons sitting up here in the conduction band. And now when I apply a voltage, I'm going to get current flow. And if I dope, if I dope it, so this is like N-type doping, and if I dope it P-type doping over here, then over on this side, it's going to be P-type. My bands are going to look like this, and I've created a PN junction, and over here I'll have holes, and now I've got a diode. So here I'm doping at P-type, here I'm doping at N-type, and this is what they do. This is how they build devices.
Okay, so that's when you put the two different junctions together, and okay. So then you never, when you doped it, you never changed the band gap. Was the band gap always?
It changes a little, but that's not what really. I mean,
'Cause
that's
you-
sort of a second, third, fourth order effect. There's a small change due to heavy doping, but really you're doping it just to introduce carriers. And if you notice, I've built myself a potential by doping it like this. I now have a potential barrier for the electrons. Right? They see this barrier that's due to the doping. So you build barriers, you build your potential profile that you want. You introduce carriers, electrons, and holes. You do all this stuff with doping.
But then you changed the Fermi level.
Well, my Fermi level is actually constant right there. Everything else has changed.
Well,
Fermi level is where it was.
you changed it from in between.
Yeah, okay. Yeah, that's true. Or you could think I moved the band down to the Fermi level. Either way you want to think about it. You could think I held the Fermi level fixed and I moved the band down, or whatever you want. It's just in equilibrium. The Fermi level is not a function of position. So, here the Fermi level is the same place as where it is here. So for that to be true, I have to move the bands up over here, move the bands down on this side. That's like a fundamental definition of equilibrium. In equilibrium, the Fermi level is not a function of position. So this is a device course. I guess you're going to be taking 203 in the spring.
Yeah.
That's what they're going to be doing in 203.
Just,
And since it's going to be taught by Elaine, who comes from Santa Barbara, I'm sure she'll do a lot of heterostructures and perhaps optoelectronic, because that's what they do in Santa Barbara. In fact, in Santa Barbara, they consider silicon to be a dopant.
wait, what?
In Santa Barbara, silicon is a dopant.
thought you dope things
Yes.
into silicon. You didn't.
Yeah,
use
but they
silicon
don't.
dope.
They only deal with 3,5s and gallium nitride and such. They don't. I mean, so for you actually dope, say, gallium arsenide by introducing silicon into it. So for them, silicon is just a dopant.
Huh.
They don't do any silicon electronics there.
So you have the 3,5, and are there huge differences? Because you go down the columns, and you can kind of can you just kind of pair the different ones with each other, and then do they have like totally different characteristics when you do that?
Well, if you stay within column 3 and column 5, you pair them up somewhat, like gallium arsenide, indium arsenide, gallium antimonide, indium
So
antimonide.
if you just like take.
But
just
when
take
you go to
one
the nitrides, then you've got a whole different animal, different crystal structure, like gallium nitride. Yeah.
So, I mean, when I'm looking at it, you have like the same valence electrons, but then you just have a different structure on when you're comparing the different ones, when you make the different.
You got to be clear what you mean by structure. Structure in what?
So if you have the different,
You talking
you
about
have the two different columns, like you have column.
3 and column 5.
This doesn't work. Yeah, so you have the two different columns, and then you take one of them out of, so in column 3, and then you pair it with the different atoms in column 5, and those have different characteristics because they're different shapes.
They're gonna
Because they have the same valence electrons, so then why would they have? I mean, they have different characteristics because of their shape.
Well, you think so? We've got gallium arsenide, right? And I'm trying to picture where they are. So gallium and arsenide. And remember, in our simple two-band model, the band gap is the difference in the on-site, the ionization potentials. The band gap was the difference in those on-site energies.
So the difference between the valence and conduction.
Well, just the difference in the simplest picture was some ionization potential for the gallium and ionization potential for the arsenic.
So when you say ionization potential, you don't mean band gap?
I don't mean band gap for sure.
I guess I don't
Just- I
understand
was just-
what would be an ionization potential then, or what does that mean?
Oh, well, the definition is you have an atom sitting alone in the universe, and it's how much energy it takes to take an electron from that atom and send it off to infinity. That's the formal
So
definition
that you
of
so the conduction
ion.
band doesn't
There
follow that
is
criteria.
there
'cause
is
it's
no
still,
conduction band for a single atom. Single atom has atomic orbitals.
Well, okay, this is another stupid question that I have. I have just tons of stupid questions. I don't know how much I.
Go ahead until the next group comes in.
So
or until I get really hungry, and you guys are free to leave.
so you have two hydrogen atoms. Let's just theoretically wise, and
Yeah.
they both have s. They both have s orbitals, and you put those together. So then, the electron. So if you have two electrons, so then do they both sit in? Because does that mean you have two different? What am I trying to say? Because you have the density of states, which comes from.
You're like confused. Okay, I mean,
Yeah.
can we just go back to two hydrogen atoms? Keep it simple. You bring them together. Initially, they just have one energy level per atom. You bring them together, right? And you get the bonding and anti-bonding energy level. Each atom had its electron. I'm going to draw them conveniently, spin up and spin down. And now both electrons are going to be sitting in the lowest level, and you've got your bonding orbital.
So you have two different states then, because you have. So when you put a bunch of different hydrogen atoms together, you're going to have. Oh, okay. So then you have all those different states. So you'll have two. So if you have a million hydrogen atoms, you'll have a million different states, but they'll only fill half of those because of the spin up and spin down. So then
They fill half. That's exactly right. And that's actually how in the DFT code they find out where the Fermi level is. In the simple DFT code we have, they just do the huge eigenvalue problem. It doesn't include spin. They do the huge eigenvalue problem, and then they know the number of eigenvalues n, and they just like sum up n over 2 and draw a line and say, okay, there's your Fermi level.
So the different states represent the different orbitals. So you have, okay, that makes sense. Okay. So if you were to apply a magnetic field across the entire thing, so you didn't get this spin up and spin down, then you would have no free. They would all be occupied then.
Usually, this energy is large, right? We're talking about big energies here between the HOMO and the LUMO, between conduction and valence. It's a big gap, your band gap, right? It's big. Take my word for it.
Yeah.
It's EV or more, especially in molecules. It's multiple EVs. And then if you apply a magnetic field, the splitting of the spins due to magnetic field is small. That's on the order of MeVs. So basically, each one of these levels then becomes an up level and a down level, and that's the only thing that would happen. You get some small splitting of the spins in each level.
You wouldn't have any. Your density of states, they wouldn't all be filled then. You'd still have half your density of states not filled.
All these states up here, which are an EV above the Fermi level, are going to still be empty. And all the states below the Fermi level will still be filled. It's just that now the states that were degenerate, right, there were two, will now be non-degenerate. One state per spin, slight energy difference.
Okay.
Before there were two spins at the same energy level. Now there will be a slight splitting of the energy levels for the up and down.
Okay, I'll have to think about that some more. I'm still a little bit.
People slowly disappear. No problem.
Thank you.
All right.
Could you possibly talk more about the group velocity as well? Like, explain.
Well, again, it's just a concept from once upon a time you learned in electromagnetics, right? The group velocity
Okay, so that's the same group velocity.
is d omega dk.
I have to think about that again.
D omega dk, and E is h bar omega. That's all we're doing. So, this is equal to 1 over h bar d e dk.